Guy ILS Montessori and School. Grade 9, Physics. Federal Board Islamabad, 2025 onwards syllabus. Summary of Chapter 3. Scalar and Vectors from Cantab Publisher Book, Federal Board Islamabad. Portion of Chapter 1, Physical Quantities and Measurement, of NBF Book, Federal Board Islamabad. Summary of Chapter 3, Scalars and Vectors. Physical quantities can be classified into two groups based on their nature, scalars and vectors. This classification is essential because some quantities require only magnitude for their description, while others need both magnitude and direction. Why do we need scalars and vectors? 1. Scalar example. Imagine you are driving and see a speed limit sign that says 30 km per hour. The speed is fully described by the number 30 and the unit km per hour. No direction is needed. You only need to know how fast you can drive. 2. Vector example. When pushing a heavy box, you need to consider not only how hard you push, magnitude, but also the direction of the push. Without direction, you might push the box in the wrong direction, causing confusion. Scalars. Definition. Scalar quantities are fully defined by their magnitude, a number with a unit. Examples include mass, e.g., 2 kg, temperature, e.g., 25 degrees Celsius, time, e.g., 10 seconds, distance, e.g., 5 meters, speed, e.g., 60 km per hour, energy, e.g., 100 joules. Properties of scalars. Scalars follow ordinary mathematical rules for addition, subtraction, multiplication, and division. Example, 40 kg plus 30 kg equals 70 kg. Scalars of different types cannot be added or subtracted, e.g., 2 meters plus 5 kg is invalid. Scalars can be multiplied or divided, e.g., area equals length times width, speed equals distance divided by time. Vectors. Definition. Vector quantities are defined by both magnitude and direction. Examples include displacement, e.g., 30 km east, force, e.g., 20 n west, velocity, e.g., 60 km per hour north, acceleration, e.g., 9.8 meters per square second downward, momentum, e.g., 10 kg meter per second to the right. Properties of vectors. Vectors require vector algebra for manipulation, as direction must be considered. Vectors of different types cannot be added or subtracted, e.g., force cannot be added to displacement. Vectors can be multiplied, e.g., force times displacement equals work. Division of vectors is not mathematically defined. Representation of vectors, symbolic representation. Vectors are denoted by boldface letters, e.g., F for force, V for velocity. Alternatively, they can be represented by lightface letters with an arrow above or below. The magnitude of a vector is represented by lightface letters without arrows, e.g., FF, VV. Graphical representation of vectors. A vector is represented by a directed line segment. The length of the line segment, scaled appropriately, represents the magnitude. The arrowhead indicates the direction. Example, drawing a vector. To draw a displacement vector of 100 km towards the north, 1. Choose a scale, e.g., 20 km equals 1 cm, so 100 km equals 5 cm. 2. Use a direction indicator, e.g., a compass, to represent north. 3. Draw a 5 cm line segment pointing north. 4. Place an arrowhead at the end of the line segment. Identifying scalar and vector quantities. Justification of scalar quantities. Scalar quantities are fully described by their magnitude. Examples include distance, measures the path between 2 points, regardless of direction. Speed indicates how fast something moves, without considering direction. Time measures duration, e.g., how long cookies bake. Mass measures the amount of matter in an object, independent of direction. Temperature measures hotness or coldness, e.g., 50 degrees Celsius soup. Energy measures the capacity to do work, independent of direction. Justification of vector quantities. Vector quantities require both magnitude and direction. Examples include displacement, the shortest directed distance from initial to final position, e.g., 5 meters north. Force, a push or pull with both magnitude and direction, e.g., 20 n east. Weight, the gravitational force acting downward. Velocity, describes both speed and direction of motion, e.g., 60 km per hour north. Acceleration, the rate of change of velocity, including direction, e.g., 9.8 meters per square second downward. Momentum, the product of mass and velocity, which depends on direction. Electric and gravitational fields for justification of vectors quantities. Electric field strength. Every charge produces an electric field in the space around it. The electric field strength at a point represents the force a positive test charge would experience. It has both magnitude and direction, making it a vector. Gravitational field strength. Every mass produces a gravitational field in the space around it. The gravitational field strength at a point represents the force a test mass would experience. It has both magnitude and direction, making it a vector. Determining the resultant of two vectors. Vector addition. 1. Head-to-tail rule. Draw vector A, draw vector B such that its tail starts at the head of A. The resultant vector R is drawn from the tail of A to the head of B. 2. Parallelogram rule. Draw vectors A and B as adjacent sides of a parallelogram. The resultant R is the diagonal of the parallelogram. Addition of perpendicular vectors. When two vectors are perpendicular, the resultant forms a right-angled triangle. Use the Pythagorean theorem to calculate the magnitude of the resultant. Use trigonometry to determine the direction. Subtraction of vectors. To subtract vector B from vector A, reverse the direction of B and add it to A using the head-to-tail rule. Conclusion. Scalar quantities are fully described by magnitude. Vector quantities require both magnitude and direction. Understanding the difference between scalars and vectors is crucial for solving physics problems accurately.